Good morning, everyone. I do hope everyone can hear me. Hello? Yeah, that's good. So I do hope everyone is doing well and that everyone had a very happy Diwali and celebrations with everyone at home. So I suppose it's 8:05 already, and maybe we could start with the class today. So, right. So, in the last two classes, we had started discussing reinforcement learning, and we had talked a bit about passive reinforcement learning. And this class will be on active reinforcement learning. And I suppose everyone has received the set of slides I shared about half an hour ago. It's just a rough set of slides, but it kind of gives you a picture of what active learning is all about, and you may refer to it during the class today. So just to recapitulate things a bit before we move ahead. Reinforcement learning was all about exploring the environment and learning what is good for the agent. The agent tries to learn what is good for it. There could be a certain mix of supervision involved in it if the utilities be available or if the policies be available early on. We can say that there is a certain amount of supervision coming in, but if the agent is all on its own, it has to kind of act in the wild and figure out what works for him. Then we have a kind of unsupervised a hint of unsupervision in the reinforcement learning. But over here, what we have to remember is there are no labeled data sets or unlabeled data sets to work on. It's all about states and actions. The agent is in a particular state and then takes an action, moves on to the next step, and then decides from there on what to do. So in passive learning, what we were doing is we had fixed a particular policy. We had fixed it that this is to be the set of states and actions possible. We could make it deterministic or we could make it stochastic, but the policy was fixed. In active learning, we want the agent to learn the policy on its own. It's something perhaps a little more inclined to a curious kind of a behavior, a more exploratory kind of a behavior. Because the problem with passive learning is that you could get stuck into doing one particular thing. If you keep doing it repeatedly because you're trying to find out which of these options are good of all the of the policy of the subset of policies that you have, fixed ones, which one is good for you? So you could somewhere maybe kind of fixate on a policy that is very good, and you don't explore anymore. But over here, we will try to include certain components into our equations to make it a little more exploratory. Right. So I'll be sharing my slides now with this kind of brief idea. And excuse me, if you might remember, I think yesterday I had shared an article on positive reinforcement and negative reinforcement in awards, and I received an email as well from one of you this morning. Now, it would be curious to see how we could design systems that would be able to take all of that together, because learning just doesn't go by one of those boxes, right? It has to check all of those boxes: negative rewards, negative punishments, positive rewards. punishments, different combinations of those. That is when we will have a complete learning mechanism happening, right? Something that works in the wild. And when it comes to learning, there are certain other things also that we have to think about. I will be talking about them in my slides as well, which is learning to learn. Right. Then we have things like learning representations. You have a concept or a perception of something of the environment. So we have to kind of bring these different things that are growing disparately all over the world, these different policies and different mechanisms. We have to somewhere start stitching them together so that we have a good learning agent. So that is something that we all have to, maybe all of us who are trying to work on artificial intelligence or are trying to understand what intelligence is all about, or are trying to build generally intelligent systems, we might try to bring all of these concepts together. Right. So now I'll move on to my slides. I'll share my screen. So I hope my screen is visible, and I'll be moving back and forth across my active learning slides as well as my passive learning slides in order to enunciate the differences between the two. So just like I mentioned a couple of minutes ago, a passive learning agent, or shall I present this so that it becomes easier? I'll present it for you. Yeah. So while fine, I'll start with the presentation, but since I have to move back and forth, I might have my normal screen on as well. So while a passive learning agent, just like I mentioned, has a fixed policy, I'll have to go back to explain, to show this, to demonstrate this in a way. Because if you see, if you look at this, so if you look at this this algorithm that I shared last, you will see over here we have this pi coming up, which is the fixed policy. Okay, this was for passive reinforcement learning, and when I talk about active reinforcement learning, you'll see it's an A over here, which is the action itself. Fine. So what we mean over here is we are trying to find out what actions are to be taken, in a way learning a complete model of the environment with outcome probabilities for actions instead of just working on a fixed policy. So in a way, this is extending the passive, one way could be extending the passive dynamic programming model as well as the temporal model that we had described earlier. So now if we have Bellman's equation over here, what you can see, this is, you might be seeing in the passive learning policy, we were not focusing on maximizing things over here in the passive learning mechanism, but the active learning mechanism, it's taking the entire cycle of policy iteration or value iteration, which is you you estimate or you evaluate if this policy is good enough or not, and then you even improve upon it. So that is where this maximization function will be. So I mentioned it over here. It is using the entire cycle. In the passive learning mechanism, it was only about evaluating if this policy is good or not. But we were not maximizing anything over there. We were not looking for the best options available over there. But over here, it's all about this particular function over here, where we are using a maximizing operation. So here I have a reference over here which you could visit, which is a very nice explanation for things, and I will also be showing it across my slides out here. So now the question is, over here, since we were maximizing on a policy, here if you see it's not a pi, which is a fixed policy. Since we're maximizing on this in a way, it apparently seems like we are taking the best move, isn't it? But does taking a best move in such an objective in such an objective manner always lead to an ideal learning happening? Or does it always equate to the real environment? That is the big question over here. Because if you think about this particular equation or what we have been doing so far, we kind of imagine that the world or the environment is a very objective or a very white and a black kind of an environment. We don't think about the different shades of gray in which the environment functions or the world functions. It's a very dynamic environment that we all live in. So just this one-to-one correlation between a state and an action may not always lead to optimal results. That is something that we all have to be very, very careful about, or we even have to remember. That's why you will see there are these soft computing strategies coming up, like fuzzy systems and rough sets and fuzzy rough sets and so on, to kind of introduce a bit of the subjectivity of the world into our computations. But there again, we apparently fuzzify things, but then again, once we put in numbers to things, once we assign numbers or values to something, we are defuzzifying it as well. But still, that is an attempt in one way to model the subjectivity in the real world. So that is what I mean over here. It is, so there was a question. Yes. Why is reward of that state not considered? We have the reward. Just the reward is being calculated over here. The reward, the utilities and the rewards are being. No, it's a product function. It's overall S dash. Yes, yes. The probability of reaching that particular S dash or the new state and the utility of that S dash. So this is Bellman's equation, and over here if we see, like I was mentioning before, this is a rather pessimistic kind of a strategy, because we are kind of just looking at a very small environment, and that too very objectively. We don't have any bit of subjectivity coming in here. Neither do we have in the other mechanisms that I will be talking about today. That could be a project that all of us could think about, but no, this is just Bellman's equation of optimality. I will be, if we come over here, what I will be coming to it. I will be discussing it. Please follow the slide. Right. So what I was saying is, these mechanisms that we have, these are very pessimistic in nature, because they just focus on a particular state and an action, but they don't take the dynamics of the environment. But taking the dynamics of the environment is something that is actually under research. That would be a good thing to say, because what is subjectivity at the end of the day, or what is actually something that the way world, that the environment functions, like the dynamics of the world, it's very, very difficult to capture it all together, because each of us are dynamic systems, right? And if we want an agent to work in sync with us, it needs to be a dynamic system as well, as good as we are, isn't it? Or at least at par, if not better. So it's a very, it's a complex system that we are working in over here. So now over here, when I do something on this lines, when I'm trying to maximize something, this is essentially a greedy approach, isn't it? If you remember from early computer science days, maybe, that if I am I am at a particular stage, and I take the maximal thing that is, or the minimal something that is available to me, I am going at local better solutions, or the best of the local solutions that are available to me. But does it always guarantee that it will work in the environment? So, how about mixing a bit of exploitation and exploration? That is a strategy that many learning mechanisms look into, which is, you know that one thing works good for you, you know it works good for you, but how about also exploring other opportunities? Over here, I would like to bring into consideration certain terms like counterfactual reasoning. That is, you might occasionally think about these, you might kind of envision these situations when you are sitting idle, maybe you are not actively doing something. That is when you start reflecting on what you have done. And then you think about, what if I didn't do it this way, and what if I did it that way? Right. So this mechanism, I know this works for me. I know I have been doing this all through, but what if I did something else? How about looking at something, a different direction? That is where the exploration comes in. So what you do is, you know, you have these actions available with you. A certain action works for you, and it has a good confidence value attached with it. But how about trying something else? So this is called counterfactual thinking or counterfactual reasoning. We do it when we are reflecting upon what we have done, particularly when we are in a state of rest. That is one way of representing it. So now we have to find a balance between our exploitation and exploration. We just can't keep exploring, because then perhaps nothing will get done. And we just can't keep on repeating things, because then there will be no innovation happening. There will be nothing new happening. So how do we arrive at this balance? This is again a very subjective question. It could work for different people at different times. It could work. And if I consider myself as an agent, or if I'm designing an agent, there is no fixed rule for when that balance will be properly achieved. It all depends from problem to problem. So now one way of representing, since we have a very limited, the computer is at the moment a very limited tool that we have with us, limited in the sense not in terms of computing power, but in terms of representation power. Please take note of that point. A computer is very good at crunching numbers, but there is not much of the semantics of the world that it can understand. So the way that we can make the real world understandable or intelligible to a machine is by, one way of doing that is by reducing any problem of the real world to an n-armed bandit problem. And n-armed bandit problem is like you give a toy n number of options, and it tries to explore all of them to see which one works better. So now, it has to decide that will it choose the one that it hasn't done before, or this particular strategy that it has never used before, or the one that is known to be a good solution. So now the question over here is, there are many such options available, right? There are many, many different ways that we can do it. But then that leads to an intractable solution space, isn't it? If I reduce my problem to an n lever, to an n arm banded problem, then I possibly have n factorial kind of options available for me. But then that is an intractable problem. It's like a combinatorial explosion happening of options available. So then somewhere again we have to reduce to a greedy strategy. That is, I try each action for an unbounded number of times to kind of avoid the probability that an optimal action didn't happen because of a series of bad outcomes. So I have a larger kind of a distribution to think about, and then I turn greedy towards maybe choosing the one that has been working. So this is, in a way, I explore, I look at all the different options, and I do them sufficiently. I try them a large number of times, and then somewhere I focus on the one that has been working better. So now over here, the question, now here again, if you see, it looks like I do an exploration, then I do an exploitation. But then I also have to go back to exploring again, isn't it? I just can't just stick onto an exploitation at the end of a series of explorations and then wait over there and then just finish it over there. I have to go back to exploration sometime again. So that is where the designing of your problem or the designing of your solution strategy is going to, the ingenuity of your design over there. That when exactly do you keep shifting that balance of exploration and exploitation? There is no fixed rule for it. It is all dependent on the problem that you have in hand and the goal that maybe that you're trying to achieve. And again, here there is another interesting question to think about is goals. What is a goal? Isn't it? At times we work, we don't even have a goal in mind. So actually, we might have to design our systems or design our policies or design our environments in this artificially, this perceived artificial environment in such a way that at times we will have goals very well defined, and at times we will not have our goals well defined, and we will be learning on the way. So I suppose everyone can kind of get a hang of how this exploration and exploitation is going to work in the real world. It's not very easy. It'll be a very fuzzy concept, but this is how it is going to be. I think there is another question. No, I didn't. And there's another question over here. Yes. Now, like I mentioned over here, that the state space is finite if you have a very small system that you're going to work on. Right. It might again, if I want to kind of reiterate what I've been saying, is if you're working on a very objective environment, say you're working on a problem of automating machines to do some kind of calculation, right? Say in mechanical engineering or something like that, or chemical engineering perhaps. There you have values which are very fixed. There you have an environment that is very well defined. Right. So over there, the state space is finite, but then again, it could be countably infinite. Here again, we have to think about the term. You can count, but again, it is a huge state space. But if you're trying to design a system that is going to work in the wild, something that is going to work in association with human beings or maybe with animals, that is when the main complexity is going to come in. That is when you don't have every state and action pair very well defined. You will have to think a little and then work on it. You can just imagine the way we function. Isn't it? We just don't keep doing the same thing over and over again. And when we do that, we use all kinds of these statements. We try to encourage people to explore. We have these education policies that are coming in all about exploration and creativity and innovation, isn't it? Because in a way we're all just doing something repeatedly, right? In production, when you're trying to produce something that is in a fixed environment, then exploitation is good. But if you are trying to work in the wild, then you have to find a balance between the two. And again, over here, that balance has to be dynamic again. So that is why we have the temporal learning strategy. I'll be coming to it in a while. Yes. So, right. So now, one way of, if you remember these dynamic programming policies and the temporal difference learning policies that we had described during passive learning, we can update the same for active learning as well by just introducing this exploration kind of a function over here, where I maximize it. If you remember in the dynamic programming equation that we had for passive learning, there was no maximization happening over there. We were just evaluating policies, but we were not looking at improving the policies. If you remember the definitions over there, but over here we're trying to find trying to choose the one that is going to be better for us. Okay, from a number of different options. So that is why we have this max operation coming up over here. And over here, interestingly, what we, instead of using just US, which was for the passive strategy, we are using something called U plus. Why? Because this function that we have over here, we have two options that it gives us. One is exploratory, which is U. This defines exploration, and this part is exploitation. If you look at the text that I've written over here, there's a large amount of text that is coming up over here. Now, when I say NSA, this is where I have my table lookup of frequencies and everything. Dynamic programming, if you remember, it is all about optimal substructures and recurrent usage of solutions. So I use a frequency value over here. I keep updating it. All of that remains the same. It's just this part that is going to change. In the earlier function during passive learning, it was just US dash, and now it's going to be U plus. What I mean over here is, I will try or I will design my function in such a way that if I'm repeatedly doing something, eventually it starts getting weighted lesser than new explorations. If you see, increasing in U and decreasing in N. So this policy, this strategy is often in most books you will be finding it as the epsilon greedy approach. I'll just show you what it is all about. Over here, if you see, I will generate a random number because in the first stage, I don't know what my utilities are or my rewards are. I'll generate a number. If it is below a certain epsilon, over here, if you see, it's an NE that we have mentioned over here. This is based on the Norvig book. So if it is less than a certain epsilon value, then I choose an action from the existing Q values. Here, Q values is the probability values or the state action pairs that I already know. Okay, so if I go back over here, if this exists, then R plus meaning something that I have already experienced before. So I'm exploiting. But if it is somewhere, if it doesn't fall into that range, then I'll go into exploration, which is finding a new strategy altogether, a new U, a new Q value for a new state action mechanism or a new state action pair. Right, so now adjusting this value of NE, that is going to be a very interesting task, because if again NE is huge, it's a large number, then you'll just keep on doing exploitation. There won't be exploration. Right. So now over here, to my mind, what I understand is NE has to be a dynamic parameter. Because if you remember from temporal learning as well, we had made our learning parameter dynamic. We just didn't keep it fixed. Right? What we were saying is, if I repeatedly do something, then my entropy or the curiosity or the surprise or the amount of information that I can achieve from it, it goes down. Right? So then my learning also should decrease from it because my curiosity no longer is being satisfied. If I can equate it to the words that we use when we are trying to learn things. So I need to adjust my learning parameter so that it always focuses on learning something new, isn't it? So similarly over here, if I just keep a fixed value of epsilon when I'm designing my learning algorithm or learning strategy for problem solving, it is to my understanding that NE has to be a dynamic parameter. Otherwise, that exploration to exploitation shift is going to be very, very fixed. Otherwise, it's just after a certain number of times, exploration is going to happen or vice versa. But it has to keep moving between the two. So now I would like to actually encourage everyone. I did come across strategies where they were actually using a dynamic epsilon. I couldn't look a lot around as well, but I would like to encourage all of you to look for these kind of mechanisms. They definitely, someone must have worked on dynamic epsilon values. So if someone comes across such a mechanism, it would be great. We could discuss this in the next class, maybe. I would like to encourage everyone to look into that because this is not the end, isn't it? So now again over here in dynamic programming, what we are doing, we have a state action and we are summarizing it across all the successor state, the source node. So there's a lot of back propagation happening from a new state to all the previous states that I have received, as was there in the passive dynamic approach, programming approach as well. So it takes time to converge. So as a mechanism of kind of avoiding this multiple, this constantly updating my entire table, we have the temporal difference learning mechanism, just like the passive. But over here, what we are doing is, if you see, we have this is a model-free strategy. Yes, the update rule doesn't change because the basic temporal difference learning over here, the basic update rule doesn't change because there too, if you think about it, I had mentioned in the class as well, temporal difference learning is somewhere in between an active learning and a passive learning because in temporal difference learning, we are moving towards a model-free strategy. We have a fixed policy, but not of the entire environment, right? So, and this is where we have this adaptive learning coming in. This learning as a function of the frequency of visiting a particular state. So now the basic rule doesn't change. We keep this fixed. But what we do is we introduce things like Q learning. Q learning is a value of doing an action A in state S. So this is an action utility pair. In this temporal difference learning equation, we just substitute this part where we just have the states coming up over here with an action utility pair. Right? If you look over here, this is the basic QSA function, and this is the dynamic programming strategy basically over here. Just the dynamic programming, same equations, just as it was over here. That is happening over here. But for the Q learning in the temporal difference model, we substitute the S's that we have over here with the QSA, which is a value for a state and an action taken together. Right. So now the entire premise of active learning was to find out which policies are going to be good for me. And policy is a mapping from a state to an action. Right. So now in dynamic programming, what was happening is if I update, if I have moved from one source state to a destination state and I have achieved an improvement in policy, it will percolate backwards across all the different sources. Right. If I show you this earlier algorithm that we have over here, if you see it, it was right, adaptive dynamic programming. It was percolating backwards to all the previous states. S was all the previous states. It was just going back. Right? It was going backwards. But over here, we don't do that anymore because this is only about the current state and the next state, just as it was in temporal difference learning and the passive strategy. Right? We are just doing these local updates, and eventually we will learn what is better for us globally. Eventually we'll do that. If you keep repeating something over and over again, you will always find these different immediate, this current step and next step working towards a global optima. That is the entire understanding. But over here, again, moving from passive to active, it is about maximizing. So hopefully we will arrive at a state action pair that makes more sense or is better compared to what we have here. There is no fixed policy. This is very important. Here we are constantly working on state and actions or new states and new actions, which is S dash and A dash, and trying to maximize upon them. Right. So this is what Q learning is, and this is the temporal difference. So now here I have an algorithm that tries to do the same. You see, it's updating the utilities or the values of a state action pair using these particular equations. It has a learning parameter attached over here, and if I want to make it dynamic, I introduce a new term like this. This book is the Bartow book that I had shared, the Sutton and the Bartow book that I have given as a resource to in the resources slides. And this particular algorithm is from Norvik's book. Fine, where they use an adaptive learning parameter. And you see that the state changes over here. There's a Q learning happening over here. It's all about maximizing things. So now over here, there are different examples available of how these these different movements are supposed to work and how many times we are supposed to iterate. There are different what shall I say, application areas of this mechanism, and you will find there is this. I have shared references over here in the next slide when we come over here on examples of implementation of temporal difference learning and Q learning and SARSA, which is the state action reward state action. I'll come to this in a minute. These are some references that I would encourage everyone to visit. But what I'm very curious about over here, right. These slides are basically from Norway, and I have included a few other things as well. I have put in references whenever I have found something that is a little more interesting, perhaps, or will help you understand or has helped me understand things a little better. I have included references over here. And if you refer to my resources slide, that is where that's the hub of all the resources actually, right? Lectures and visualizations and tools and books and other articles and everything. And if I have come across something that has helped me understand something a little better, I've included it over here. Okay, so this is how it is. But now what I do feel is this is all very good theoretically. And perhaps when I'm trying to design a system, if slides are there, it will be better. Sorry. If slides are there, it will for all the topics. Yeah. I'll try to. I am designing these slides, so this is like a work in progress. Not all my slides are ready yet. And very honestly, I haven't taught this subject before, so it's all about learning and trying to kind of explain in a way. So this is a nice experiment over here that is happening because what is happening through this exercise, if I might share it with you, is I too am doing a reinforcement learning over here. Because when I am trying to explain something to you, or when I'm trying to excuse me, I think there's someone who has come. Please give me a minute. Please give me a minute. Someone who has just arrived. Hello. Yes, I'm back. I'm so sorry for this interruption to the class. A gentleman had arrived to talk about certain things. I'm so sorry. I'm so sorry. Yes, there was a question on the epsilon, if I remember. And I will go back to what I was saying about my own reinforcement learning for the class. Reaches should reduce to zero to ensure more exploitation happens versus less exploration. Now, this is something that we can't actually very fixedly say. If I want to design a very dynamic system, if the terminal state is fixed, if I know that this is my goal exactly, then perhaps having a fixed epsilon makes sense. In fact, exploitation makes sense, like I just mentioned a couple of minutes ago. But if I'm trying to design a system where the goal isn't fixed itself, or I'm trying to learn small goals towards a big goal, right, even down to the atomic levels. If you remember from the very first class, I had given an example where when a baby is trying to learn, you might be seeing babies babbling, right? They play around with their hands, they throw their hands around, they throw their legs around. All of that is an evolutionary mechanism in order to learn the connections between the motor neurons and the sensory neurons. Right. So when a baby moves its hand for the first time, say from left to right, it keeps doing it repeatedly because those neuron connections get strengthened. That particular motor neuron, that action happening. So it doesn't have a goal at that moment. It just does an action, and it kind of, if I consider its knowledge repository, a kind of a rule gets written over there that if I move my hand from here to there, this is what happens. So it doesn't have to be a fixed goal, Right. So in order for that goal to get established, that I can move my hand from left to right or right to left, there are a number of neuronal parameters that have to be adjusted in between. There are many, many such parameters. I can't always put the same force when I'm moving my hand, right? There are different forces that have to be applied. When I'm trying to move an object, that is when my forces have to change, my muscular the pull and the tension of my muscles have to change. So over here, if you see, it isn't about fixed goals. It's about learning something and then transferring it onto different things. So when I know that my goal isn't very fixed, then perhaps an adaptive epsilon would be of better use. Not something that is fixed or something that eventually goes down to zero, but something that is more dynamic in nature. That is my understanding. Because if we think about it, there is a lot of transfer learning also. But once we are doing reinforcement learning, we are trying to learn about the environment, right? And we are trying to build a knowledge base upon that, a knowledge base of state and action pairs. Isn't it that if I do this, if I am in this state and I do this particular action, I will achieve this kind of a result? It could be a negative result, it could be a positive result, right? This is my knowledge base that I'm trying to build up. I'll expand upon this a little as well. Because over here, what we have to think about is a procedural versus a deliberative knowledge base. I'll write that in chat as well. Procedural versus deliberative. What happens is a procedural database or a procedural knowledge base is something that you learn without being aware of it. Right? You just happen to learn it, but you are not sure of what is happening. For example, riding a bicycle or learning to swim or learning to lift an object. Not weightlifters. Weightlifters do it deliberatively because they use deliberate strategies in order to learn how to lift weights effectively. But you and I, the common man, we don't have any deliberative goals to lifting weights within a particular time and lesser number of jerks and all of that. We don't do that. So our learning is procedural. Why? Because we don't know the amount of force that our muscles are employing in order to lift an object. We just do it. Right. I hope this is understandable. So I have a procedural knowledge base, which is more about the bigger picture. I don't know the different the smaller states or the smaller state action pairs that are happening, but I learn that if I do this, this is going to happen. Fine. And deliberative learning is when I try to find the semantics between the state and the action pair. Okay, like if I do this deliberatively, then I will do that. Or you learn because you have a goal in mind. Okay, so there is a difference between these learning strategies as well, between the knowledge bases that we are trying to build. So all that I have been describing over here, these are just overviews or umbrella terms, basically. When we are trying to design these or actually implement these algorithms for the real world, it's going to be a very different experience altogether, because we have to think about these procedural elements, common sense. What is common sense? If I'm trying to design an agent that is going to go beyond the mundane, right, then I have to think about common sense as well. Common sense learning, common sense reasoning. And where does common sense fall into? Does it fall into the procedural level or does it fall into deliberative level? In fact, deliberative learning, which is repeatedly I'm doing something for a particular goal, it kind of becomes procedural after a certain number of reinforcements. Right. Initially, you had learned to do something, like for example, learned to write the alphabets. That was a deliberative learning happening, but now it has become procedural for you. You don't think about it when you write the letters, right? So there is this constant movement happening between procedural versus deliberative versus learning just actions and state action pairs. It's a very, very dynamic system that we are all working in. In fact, uh, even these very objective systems that we are working in, they too tend to fail when they do not have sufficient parameters taken into consideration. For example, the friction, then the humidity in the atmosphere or in the air around. When you have these systems that have to be very precise, like clinical devices, which have to be very precise in their work, then you have these kinds of dynamic systems to deal with. Right. So if I'm trying to design a reinforcement learning model or a reinforcement learning algorithm that is going to work on such a precise device, then I have to think of large number of parameters, and each one of them maybe has to have different epsilon values. And these epsilon values again have to have a global epsilon function working on them. Is this making sense to everyone? This is what I'm very curious about. Because this is a very, very complex thing that we are all trying to do, and we are all trying to reduce it to numbers and equations and simple state action policies. But there is a lot more that is happening beyond just this. I hope everyone can kind of feel it. Because now coming back to the lecture over here, I won't call it a lecture, the discussion. Sorry. If you see the past slide, which was in Q learning, it was we are trying to maximize across all the different the immediate successors and the action pairs. But over here, which is the SARSA learning, this is more about observations. If you see here, Q values, these are observations or estimates or a hope that this is going to happen. But in SARSA learning, the QSA that is used over here is 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 derived after the action has actually taken place. Okay, so this is more about learning from observations. Over here, I have my entire this set of observations available with me. But SARSA learning is all about that particular action that I have taken. Right? This is a more, shall I say, a more reduced version in a way. So over here, if you see, I have written it over here that Q learning is more about observations, while the SARSA learning role is more about an actual occurrence. There was an example over here that I wanted to show you. I think it's this game, yes. Over here. Right. They have these two algorithms written over here, and I've even put them on the slides as well. So over here, if you look at them, here we have this maximizing across all observations happening over here, and over here it's about this particular action. And if you think about it, I'm also updating it. My action to be is the action that I have just taken. Over here, we don't do that, because I'm just working on my observations. I'm not working on my actual actions. But over here, it's a little different. Fine. So that is why this Q learning is called off policy, because my actions may not always be in line with the policy that I'm thinking about. I am in a particular state, and I have a particular successor state and this action happening. Okay. But and I'm trying to choose the one that has the maximum value amongst all the utilities available. Utilities on state action pairs, which is very important to remember in active learning. But on SARSA, this is called on policy because I'm focusing on a particular state action pair together, right? A particular combination together. This is the basic difference between the two. That's why this is called an on policy. This is called an off policy strategy. And here they have an example. I have shared this in the slides as well. Oh no, I haven't shared. I'll put it up on chat for you. And I'll also put it on the slide. Everyone can actually click on it to see how it's working. I would encourage everyone to actually visit these websites because it's not always possible to have everything done in detail in the class. So I'll keep sending you these references to look into. Fine. So now the question is, all this looks good in theory, but how do we actually implement it? So here there are these examples over here which show how these values or how these updates are going to happen. But what I would like to encourage everyone to do is actually implement these and try to see. Print the different iterations, print the different rounds of updates that are happening, and then see how it works, and then understanding it. I would like to encourage everyone to do that. Here I have the same algorithm. So now these are all the different questions that I have been talking about. This learning to learn, unlearning, relearning. This is in fact another question that is very important when it comes to active learning again. You have a state action pair that has been working good for you. This exploration exploitation trade-off, that is what I want to focus on over here. Something that has been working good for you for a large number of instances, but then say an environmental parameter changes. And then that particular state action doesn't work good for you anymore. So then again, there must be something happening over there for you to unlearn what you have learned and relearn it again. Isn't it? Does that make sense? I request feedback. We have about half an hour, so let's try to discuss this amongst ourselves. Say you have attained a certain number after a certain number of trials, you have come to this conclusion that a particular state action pair works for a particular environment, right? So, and your exploration strategies are also fine, but say this particular state action fails because of certain changes in the parameter, then what do you think we should be doing? Then how do you think we should be changing our algorithms? How do you think we should be doing that? This is I would like to know your thoughts on that, because that is something that we will have to actually design in real. And any thoughts on that? Relearning from start. Yes, some more exploration. But how are you going to make it do that? It has to kind of, it is kind of going back a few steps. Adapt, yes. I think in our equations, when we have to design for an environment, we have to include our states actually. This is what I wanted to arrive at actually. These states that we are using over here, this is where a certain amount of adaptivity has to come in, if you think about it. Because a state is not just going to be a function of one tuple or one parameter. It definitely is going to be a function of many parameters, isn't it? when I'm drawing a state transition diagram, each state that I'm in is a function of many parameters, right? So at that particular juncture, if example of parameters could be, like for example, this machine design thing that I was saying, it could be the humidity, it could be the friction, it could be other such parameters, names of which I don't even know about. These kinds of parameters, environmental parameters, or say when you are working, your state of mind, you have your own state transition diagram, right, as a human being. So your own state of mind is a function of so many parameters. Your interaction with your colleagues, your health conditions today, your interaction with people at home. It's an example of so many parameters and that particular state. So now when we are designing a system, as of now, we have a very of most of the systems that we have in real or existing at the moment. Right. I'm just coming to that point. We have a very fixed number of parameters during machine designing or even in our learning algorithms. The parameters that go into defining a state or the parameters that go into defining an action, they are very fixed. It's only when something that happens just um, that does not convene or does not conform my idea, that is when the change happens. Like for example, I might have designed a machine with 5 parameters for defining my states. Then one day something else happens, and then I realize that I should have defined my state using 6 parameters instead of 5. So until uh, that uh, that particular that situation arises, maybe I am not aware of the parameters that I should be thinking about. Right, the transition probabilities could change with parameters. They could, because each combination of parameters is going to give you a different state altogether. Or as in rough computing or rough sets, what they do is they take an umbrella over these different parameters. Right, different parameters that are within that function within an upper level and a lower level. Within a certain level, you kind of club them together under one granule or one state granule. Instead of having n number of states for every possible combination, we can have granules of states. But that again is for ease in calculations. That is just for ease in our calculations and perception. Right. So again, so that means so if I have designed a system where I see that a particular state action pair is not working, so intuitively, what my understanding is, a state action pair. This is an active learning mechanism happening, obviously, because there is no fixed policy over here. A state action pair has been leading to high rewards. Okay, high utility. High Q values. I would rather use the word Q because that is what we have been describing so far. Leads to high Q values, and I keep using it. But then one day, a certain parameter value changes, and my function. Now, that change in the parameter is perhaps not something that I had anticipated or is not in my state space. So then the question comes is, can I transfer some of my learning to learn this new state? So that is where that question of common sense comes actually. Instead of and like this, the suggestion that was they're learning from scratch in one of the chats. If I remove everything and I start again, it will again take me a long time to converge to a solution, right? So how about transferring some learning into this new learning? Or maybe I can do a number of iterations in this current new value state that I have come up to. I do a certain number of iterations within this, since now my curiosity is high, right?
given this particular state action pair, this new unexperienced state. How about if I do a certain number of iterations over here and I try to fix up in my mind if this is just a chance happening or is this for real? Or does this state action pair no longer work, or is this just a sudden happening? This is actually where these probability functions and frequency functions, these frequency values come into play actually. In these learning equations that we have been discussing so far, we have these frequency values, right? So maybe one strategy could be in my active learning policy that I repeatedly perform this experiment now. This is a new data that has come in. My state action pair is not working as earlier. How about I repeat this particular experiment? Because now at this phase, this is a mix between active and passive learning. If you think I have a policy defined for me, right? My policy was fixed because it was doing good. But now I'm trying to learn more out of it or gather more information out of it. So I do certain number of iterations and I try to figure out that is this just a chance happening or did it happen for real? See, after P number of iterations, here again, we don't know how to fix P. But say I have some strategy again to fix a number of iterations, a number of trials, and I see that this is for real. The world has changed. Something in my parameters, something has gone wrong. So then the question comes is it just a parameter value? Because parameter values might have already led to other states. So this is a new parameter value coming in, if you think about it. This could be a new parameter value coming in, or it could be a new parameter altogether coming in. So again, so now the question comes is how do we define systems with dynamic parameters? Dynamic parameters in the sense not just values being dynamic, but the number of parameters being thought about is dynamic. How to decide which learning do we transfer? Exactly, this is where the encoding of the semantics into the learning is necessary. How to decide? This is a fantastic question actually. This is where learning of the semantics, something that we were not doing in direct utility estimation, we were not focusing on the semantics between state action and state pairs. We were not doing that. But maybe in our knowledge base, this state action, this combination that I'm storing in my knowledge base, maybe I have to encode the semantics of it in some way. I don't know how, and I don't have an idea at this particular moment, but there should be some kind of a semantic of or some kind of an understanding actually that why this state is leading to that action and this is working good. Some kind of understanding perhaps is necessary over here. So then only will the transfer happen. This is actually a fantastic question. Because if I might just go back to to a couple of months ago, actually a year ago, my entire PhD thesis was trying to design a model of understanding. So now we come to this question again: is how do we model understanding of state action pairs? How are we going to do that? Because now this makes sense, right? I have to, if I want to do transfer learning, but then how do I encode the semantics of state action? This is just not numbers. These are parameters, they're different interactions all together. But how do I encode it? And how does the system understand that it has understood? Isn't that a question again to think about? How will the system understand or say encode reasons or semantics? I'm writing this in chat for everyone to think about. And is how will the system represent its own qualia. I can use the term here, qualia of understanding. Qualia is the sense of understanding. Right? Like if someone is explaining something to me, we said, I've understood. So what is that makes me understand that I have understood something? So in these active learning equations that we have been designing, over here what we have figured out now is that our states, they have to be a combination of many parameters, right? If I'm trying to design for a dynamic environment, and most environments are dynamic. So we have n number of parameters to think about. We have an epsilon to think about to balance between that exploration and exploitation. And now the question comes is, how do we do transfer of information that I have gathered from a particular set of actions to, this is now, I can actually expand this to intra-system transfer and inter-system transfer. When I'm designing an equation for a particular system that will be just doing one action or one big action, then it is an intra-transfer that is happening, right? One state action pair to another state action pair maybe. But if this is going to be a global or a generally intelligent agent, then this may have to transfer its learning from one domain to another domain. So then we have bigger semantics to think about. But first, let's keep that as a big question in our mind. But let's focus on this intra-transfer thing first. How will we ensure that this transfer is happening? So somewhere we maybe have to encode reasons or semantics on these little things that are happening. So now coming to the molecular level, when we are thinking about neuronal learning, the one that happens in our brain, we aren't sure of how reasons are mapped there, but definitely something is happening because we learn to reason. We learn to figure out somehow that this is making sense. But how do we do that in these learning equations over here? Because clearly this is good at an umbrella level, at a top level, but there is far more that is embedded or has to be embedded in these learning equations, whether it be Q learning or it be SARSA learning. If you think about it, even in SARSA learning, over here, I am using this, I come to this conclusion that I use this particular action. I do an action, I use a utility and I update. Right, but if I don't encode a reason over here, then is learning actually happening? The semantics, if I don't encode it over here, it's just not the parameters. What do you think about this? We have about another 10 minutes to think about it, but does anyone have any ideas on how this intra-system transfer could happen? Because that is important if you think about it. When I am learning actively, and there is a bit of passivity coming into my learning when my policy is getting fixed. But now I have to, sorry. Hello, can everyone hear me? Okay, fine. So if everyone can hear me, so now the question is, right, so does anyone have any ideas or any thoughts on how this needs, right? That is good, but how are you going to initiate that transfer? That is my question. We've discussed on states, we have an action, but how do you transfer? How are you going to do that? Any thoughts on how you could encode the semantics? Any thoughts on that? possible states can be equivalent. They could be, yes. Policy parameters need to be transferred, but just parameters, the model parameters needs to be transferred. How? To Ranjan Kumar, states, actions between different domains, yes. But any thoughts on how you would do that? Any thoughts coming to your mind on how we could do that? Model policy parameters, yes, they need to be transferred. But my question is, how are we going to do that? Right, that is entirely what transfer is, bootstrapping from what we have already learned. In fact, all our learning mechanisms over here, in a way, they are bootstrapping because they are using previous utilities. They are using experiences of rewards. They are using that. But what I'm trying to arrive at is storing the semantics of these rewards, the meaning of these rewards, just not the values. All this while we have been talking about values, right? It's all about a value that we arrive at the end. But can we always just arrive at numbers? This mapping state action pairs, policy parameters. But maybe I was just thinking. This is just an idea, and I would like to hear your thoughts on that. If history of obtaining rewards and compare across models, right? That too is something that we could do and compare across models, right? We could these are indeed strategies. What I was thinking about is going a little beyond that, maybe. Right? We could definitely think and go through filters. Maybe we could do that. It would be interesting actually if we could take up a problem and design it from scratch and then see how it happens. Any ideas on any problems that maybe we could think about and we could use it iteratively or recurrently through this subject? Any thoughts on that? Maybe then it would be easier. Maybe I think to think about transfer learning and how do we update our states, and in fact the kind of parameters that we need to work on defining our states. As of now, usually there are experts. We have domain experts who try to give you parameters to define your states. It's usually that. But if the system has to learn the parameters on its own, and how about that? The system has to learn a parameter on its own. So, how will it name its parameters? These are certain questions to actually think about when you are trying to design a system from scratch and you maybe don't have a domain expert with you. Now, the transfer learning that I'm trying, right, some ways to annotate, that is a good thought actually. Self-learning or reinforcement learning is in a way self-learning. It is in a way self-learning. Over here, the transfer learning that I'm actually trying to talk about is uh, using information that you have gathered in one area and modifying it for another area. That is what I'm trying to arrive at. Some ways to annotate, that is good. That we can do. But how do you make the annotations understandable or intelligible to a machine? How will we do that? That these are some other questions to think about again. And I'm actually very we're very happy with this entire discussion that is happening. Aren't policies transferable across models in RL? That depends on how you design it. You need to design that. They don't have to be transferable. They don't need to be transferable, but you can design one that is transferable. And in fact, it would be good to have one. So that is where, so if you're doing it across models, but if it is for the same problem, so then it is basically an intra-system transfer that is happening. It's maybe just about, can't it be done via imitation learning? Now, imitation learning, to my understanding, is just getting the initial concepts. You see something and you try to imitate. But are the semantics getting stored? Because, for example, if you are trying to learn cooking from YouTube, you are doing imitation learning, but does it work all the time unless you have a history or you know cooking actually? So, if you are trying to design a system that is going to learn, say, through one shot or just through a video, it will learn that it has to do this to do that to arrive at a certain state action. But is it actually learning if the semantics aren't coming in? If it isn't doing some reasoning over there? Like, for example, you are watching YouTube to learn to make a recipe, so you're imitating it. But if you don't understand how tastes work, or how fire works, or how all the spices together work, then will it actually be a learning happening? You will learn from experience. That is true. Right. Generalizable, maybe yes. Somehow they have to be generalizable. So maybe information from percepts, yes. Yes, definitely. So actually, these statements that all of you are doing, I would like all of you to actually think about them, encourage you to explore these policies in detail. What is the research that is happening in these areas? Because here, if you think about it, we are actually going a little beyond just numbers now. We are actually moving into the domain of the abstract, right? Not just numbers, but we are actually moving into concepts of natural language. We are also moving into concepts of abstract representation, representation of the real world. So we are moving a little away from numbers also. So numbers are good if you have a very fixed system to design, but when you're trying to do active learning in the real, then maybe we have to look beyond numbers. These are actually fantastic points that everyone has written. So, any ideas? At this, we just have about 2 minutes before the class ends. And this has been a fantastic discussion, in my opinion, but I would like to know your thoughts, because what I've done is I've just given you the umbrella terms, but then thank you for the reference. I will look into it. I will definitely look into the article that you have shared, and maybe we can discuss about this tomorrow, because in fact the next topic that we have is on generalization. So we'll be discussing generalization tomorrow, but I suppose you're getting hints of it, right? On generalization of functions on generalization of learning towards a global learning happening. I will definitely look into this article. Thank you so much for sharing. And the class is almost coming to an end, but I do hope we have sufficient food for thought. We know our equations, we can understand fairly roughly that when to use what, but how do we actually use them? And is the learning actually happening? And how do we extend these systems to just beyond equations to actually representations of the world and learning from them? I hope everyone is curious about them now at this point in time. I do hope everyone is. And I would like to encourage everyone. This article that has been shared, I will definitely be going through it, and maybe all of us could actually go through it and discuss. And tomorrow we will have a small quiz on active learning. We will have it uh, towards the end of the class, just as a revision, right? Just to kind of uh, get a feel of whatever that has been done in class, these equations, whether they are making sense or not. We will have a small quiz on that. But quizzes are not the end. Our aim is to design a system that is going to do all that we have discussed. Right, so let's keep thinking on all of that. Let's keep thinking. Let's discuss it in the next class or maybe the class after that. And it's 9:31. I will not take more of your time, but I do hope everyone is getting a feel of these different terms, of the learning, of the different kind of strategies that we need to think about, how we define our states, our actions, even defining actions. That is again something that we have to talk about. I hope everyone is getting a feel of that, and I will stop the class here. Take quiz in the beginning of the class. Okay, we could do that. Maybe we could do that. We'll take a quiz then, say from the classes at 8. So right, so then we can do that. We can take a quiz in the beginning of the class. If does everyone agree to that? Taking a quiz in the beginning? No. So it's mixed. And majority say no. So here there's this majority saying no and some saying yes. Right, I'll talk to my TAs once because actually they had suggested taking it at the end because when it is done in the beginning, it affects the class. That is what was their observation, and so we thought about right. All the quizzes will be graded, right? They will all be graded. So it was their observation that it was affecting the class. So that is why we shifted it towards the end. But let's see. Let's try for 2 quizzes at the end, and if it is not working for everyone, we can middle. That might be tough, isn't it? Won't it disturb the flow? This is a fantastic observation. Smooth transition of power to the majority. Right, taking it in the middle might disturb it more, I think. Right. It's already 9:33. We won't stretch this class. The TAs are already working on designing assignments. Their exams have just got over. So I suppose we will have assignments given to you in good time. They will be given to you in good time. So it's already 9:33 and I don't want to make the class further delayed, but I just hope we have sufficient food for thought and we can take this forward in the next class. And thank you all for coming and making this discussion really very engaging. We discussed so much within the environment of active learning. Right. Thank you, everyone. Thank you, everyone. And please feel free to ask questions and everything. Let's discuss and see what we can arrive at. Thank you. Thank you, everyone.